Midas FEA for structural engineering and Midas GTS and Midas Solvers for geotechnical engineering. So it is specializing in almost hello, yeah, is it clear now? Okay, so it is specializing in a lot of areas. I mean, it is specializing in almost all area of the civil engineering. So it is covering the normal superstructure, it is covering bridge, it is also covering geotechnical. So we have solutions in all of the respective fields. Okay, so what is Midas Civil? Okay, so majorly the graphic user interface of Midas Civil will look more or less like somewhat like this. So we are having one main menu. So I will explain the graphic user interface once we come to the once we demonstrate the things. Okay. So anyhow, we'll just go overview that we have a work tree in which you can see all the details of the project that you have done, all the sections that you have created, all the materials that you have created. Similarly, there are many ways, around 7 to 8 ways to model a bridge. You can, according to the efficiency, according to the level of modeling that you have done, according to the practice that you have done, you can adapt to any specific type of modeling. Also, we have a message window, so you can type in your message window. It prompts to you if some error is happening or something is happening. It will prompt you. Okay. Also, we have a customizable task pane. So I will be explaining these things while I am doing the demonstration. Okay. So the application areas, the major application areas for Midas Civil is, as you can see, that Midas Civil can handle almost any kind of bridge, so a wide range of bridges. So it can handle from very simple culverts or a RC bridge or a PSC bridge to a very complex cable stayed or stayed segmental bridges, or suspension bridges. So it has got quite a bit of technology also with it. So it can do post-tension, stage construction analysis, 3D tendons and tendon losses, dynamic nonlinear analysis. So it has got quite a bit of variability when it comes to uses. So what kind of bridges that Midas Civil can handle usually? So as I told you, it can handle from very conventional bridges like culvert, frame bridge, slab bridge, precast, integral bridge, steel plate bridge, steel box girder bridge, to stage segmental bridges like balance cantilever, incremental launching, movable scaffolding, precast segmental, full staging method bridge, to very highly complex cable stayed bridges, extra dose bridges, suspension bridges. Okay, so it can handle various types of bridges. Similarly, for all these types of bridges that I have shown, I mean, you can go about modeling from scratch. That is, you can create your nodes first, then elements between the nodes, right? So you can create your model manually from the scratch. But in spite of that, we have wizards for almost all those bridges that you saw behind. So those wizards are built-in templates that you have to enter just a few data inputs into it, and your bridge will be complete in front of you. So it reduces quite a bit of time, and it gives you a flexibility also. It is not like that you cannot edit it afterwards. So you have the flexibility also. Okay. So we have a lot of wizards concerning segmental bridge wizard, suspension bridge, RC culvert, box culvert, RC box culvert wizard, RC slab wizard. Okay. So we have these kinds of wizard there. Also, we have various kinds of inbuilt section properties like pre-stress and post-tensioning concrete box sections. So in that, I mean, the section database is quite wide, and any type of section you can model it inside Midas Civil only. So if you have variable slopes for the section, also you can enter the section with the help of coordinates. If you have your coordinates for the section, then you can enter it directly. Okay, so I mean, quite a bit of flexibility is there while you define a section in Midas Civil. You will find it yourself when I will be defining one section. Okay. Other than that, if you have a very complex section, I mean, if you have something like which cannot be defined in Midas, then almost yes, certainly you can import it from AutoCAD and into Midas Civil. Okay, so any kind of section you can import into my AutoCAD. Okay. Similarly, we have some standard sections that are for ASCII code, usually used for American code. Some standard sections are there. You can change them, change the properties of the sections also. And we have tapered sections. I believe most of you are aware of tapering, how the tapering is done. So usually what happens is that we do tapering from one end to the other. Like if I want to press something like this, suppose I want a tapering. Okay, something like this tapering I want. So usually what you have to do is that you have to create a lot of sections at small interval and then create tapering for each and every element, right? So this is the usual procedure. In Midas Civil you don't have to do anything like this. You just have to give the ith property, that is this is the ith property. Similarly you can give the jth property, this is jth property. Okay, and it will taper in between. So it uses a reverse philosophy. First it will taper in between, and then if you divide into a number of sections, then it will give you the section properties at each and every section that you have defined. So tapering is quite easy in Midas Civil. You will find it quite easy in Midas Civil. Okay. So next comes the flexibility of defining a composite section. Usually what happens is that when you have a slab plus girder system, then either you go for a plate element plus line element modeling, or you go for a complete plate element modeling. But in Midas Civil we have a special type of section that is called composite section. So in composite section you can define both the slab, that is here, you can see here, that is the slab here, and the girder property together. So you can define both the slab and the girder property together. Sorry. Okay. So also you can control, like in composite sections, usually what the problem that we face is that while doing construction stage, we first define the girders over the bearings, okay, and after some time we lay the formwork for the slab, then we pour the slab over the formwork. Then also, even the slab is present in its wet form, we do not consider the composite action there. Okay, so we consider the composite action only after the slab attains its green strength. So we can actually control this in Midas Civil. What you can do is that you can control when to activate the composite section, when to activate before composite, when to activate the after composite. So you can control. So you can see the properties here, like before composite, what is the before composite, what is the after composite action. Okay. This is what section property calculator I was mentioning. So if you have a very complex section, so in that case you usually can define that section in AutoCAD and import into Midas Civil. Also, the section property calculator, as it is shown on your screen, is a special type of tool that is Midas Civil is having. In that, what you can do is that you can draw your own section also. So it is not like that you have to complete a line on AutoCAD. You can draw your own section in this section property calculator also, but only for the purpose of importing the section into Midas Civil. Okay, so you can create your own section here. You can import any section from AutoCAD. Okay, so this is an example where a section was created in section property calculator. Okay, and then it was imported in Midas Civil. Okay, so it comes as a prismatic section, and you can design these sections also. It is not like that you cannot design. You can design these sections also. Okay. Effective width calculation. This actually comes in very handy when you are doing a continuous press, because in case of a continuous press, you have supports in between, and wherever the continuous supports are there, you will have a hogging moment there, right? So the complete section stiffness is not coming into effect. So we have to take a scratch section stiffness. So in ASCII code, in Euro code, they have a special call for effective width calculation. So according to ASCII and Euro, in the latest version we also have Euro code. So according to ASCII code and Euro code, it will automatically calculate the effective width. Okay, so it will automatically reduce the stiffness at near the support locations. Okay, but in case you want to do it manually, you can do it manually also. So we have that system also that you can do all things manually, and you can allow the software to do it with respect to the code. Moving load again is a 3-step process. Majorly it's a 3-step process. So you can define a moving load code, like you can choose a moving load code, like suppose you have chosen India. So according to different moving load codes, the whole menu system will change. Okay. So then after you define moving load code, you have to define the traffic line lanes. So you define traffic line lanes. Then after you define traffic line lanes, you define a vehicular load. Okay. So this way, you just 3-step process you have to do. First, you define moving load code, define the lanes on which the vehicles will move. Then you just define the standard vehicular load or user-defined vehicular load. So class 70R, class A, and finally you do a moving load combination, running class 70R, running class A together like that. Okay. So this I will explain you. Okay. So this feature is majorly for Astro code. So what happens is that in Astro code, for negative moments they have an optimizer. So what happens, wherever the hogging moment, wherever the continuity is there, for that negative moment, Astro code has a clause where you have to place 2 vehicles at a distance of around 25 feet and you multiply it by 90% of the load that is coming, and for that you find the negative moments. Okay, so that thing can also be done in moving loads. So you can define the lane support negative moments. Now we come to the analysis capabilities. So we get our tendon pre-stress losses. In the construction stage analysis, basically means that we are doing a time-dependent analysis. So now, the moment I include time, I have to include creep and shrinkage. I have to include compressive strength. So in that case, the construction stage analysis becomes very important, right? So whatever construction sequence that you are having, whatever age that you are having, whatever tendons that you have, at which stage you have placed the tendons. Okay, when the tendon was placed, what is the strength of the concrete? So everything is controlled by the construction stage that you define. Okay, so in a way we do a construction stage analysis. Okay, so we get the tendon losses, we get a tendon time dependent loss graph. Okay, so we get immediate loss also, like you can see here. Sorry. Okay, you get immediate loss and both elastic deformation and both long-term losses. Okay. Moreover, we can get an output at various locations. Like for the PSC section, it is not like you can get only at the top and the bottom, like the positions that are shown here. So you can get the stress output at almost each and every position: the haunch position, the bottommost fiber, the topmost fiber. Not only that, it's not limited to this, but virtually you can get the results at most any location you want. So at any location, like anywhere, if you want the output to be here or to be here or something, you can find the output there also. Okay. Next comes the design features. So in design, currently we are having PSC design only for ASTO LRMD 2012, 2007 Eurocode. And also for reinforced concrete, we haven't included yet IRC 112, but we are doing it for IRC 21, and steel design we are doing it for IRC 800. We are in the process to include IRC 112 also. We have already included IRC 112 for the creep and shrinkage and relaxation losses. So very soon you might see that also. Okay. So PSC design as per ASTO code is you have a menu where you can control the design features. Okay, so you can select the tendon type, the exposure factor, the output parameters. Okay. Similarly, PSC design as per ASTO LRB 2012, so you can get the cross-section stress design results also in tabular format. So you can get the area of steel from there. Okay. You can also enter your reinforcement into the section. This is a CF10 design table. And finally, when everything is over, you also get a very good, full Excel table, Excel design report generated by the software itself. So it not only gives the formula, it gives everything, it gives an account of each and everything that has been done in the software. Okay, so all the coded formulas, what formula what formula it has used to come to a solution, everything will be shown in the Excel table. Okay. So now what I will do is that I will quickly just show you how the modeling is done in Midas Civil, how easily you can do it. So what we will do is that we will model a simple bridge, something like this. So it's a 30-meter bridge, okay, and so it is simply supported, it is having simply supported conditions, and we will do a tapering from the support section to mid section, and similarly from mid section to support section. Okay, so we'll have in all 4 section properties. Okay, so what the first few properties, this will be your support section. Okay, then from here we will taper it to mid section. Okay, sorry. So we will taper it from support to mid, and this location. At this point, we will give totally mid section. Okay, and this again will just give mid to support, and finally we'll have only support section again. So this actually should be support to mid. Okay, so in a way I will define everything again. Okay, so in a way we will just do this simple bridge. Also we will be giving some tendon profiles, some straight tendon profile we will be defining, and this will be the section properties that we'll take. So how easily can we define these section properties? Okay, so first of all, I start with Midas Civil. Suppose I'm taking okay. So here we can, as I was explaining you before, I will explain you the interface of Midas Civil. So Midas Civil has an interface. This is the main menu that you are seeing. Okay, these are all the menu items. Okay. Similarly, you will get one tree menu like works, tree, groups. Okay, and I'll just explain in the already done project. Okay, so in the tree menu, as you can see here, you can find out from this only what all thing has been done in the project. Okay, so what materials have been used. Okay, so how many elements, how many nodes, how many beams, beam type element. Okay, what is the material type that we have defined, what is the tendon material property. Similarly, creep and shrinkage, the section property, the reinforcement that you have given. Okay, supports, so you can see the supports also. Okay, similarly static loads, so self weight, SIDL. Okay, the tendon property. Okay, so this way you can define it quite easily. All you can, from the tree menu itself, you can find out what has been done in the in the file. Okay. Also, I was showing you before, you have a lot of wizards. So I'll just open a new project. So you have a lot of wizards like FCM bridge, so free cantilever bridge. Okay, so you can import it. So this is already having the full layout in front of you. Okay, so you can import any material property, which is import it in from any previous file. So you can just import it directly. Okay, Similarly, number of peers, you can choose 2 peers, 3 peers, how many peers. Peer section, again, you can simply add a section, like user defined section you can add. Okay, and then you can define the stage duration also. Suppose 30 days duration you have given. Number of peers you can define. You can define cast in situ or precast. So cast in situ and precast will have a difference in construction stages. Okay, so I mean, what happens in cast in situ is that it will include the form traveler load, it will include the wet concrete load that is coming for the next segment. All these things it will include. Okay. Similarly, you can give a plan radius also. I mean, plan curvature. Then you can, for peer table placing, you can define at which day, what is the age of peer tables. Okay, so you can define from there. Similarly, key segment, so you can define it from here. What is the key segment, age, and everything. Peer table, suppose 40. 60. Okay, so this way you can define member age also. So what is happening is that the first peer is being constructed on the day 1, second peer is constructed 60 days after. So this way it will also take, because ultimately when we are doing FCM bridge, FCM means a balanced cantilever method. So ultimately when we are doing an FCM bridge, we are constructing 2 piers at different time period, right? So whatever time load that is there, due to the time, whatever extra forces that has come, then it will take it directly from here. Okay. Then we can choose the section directly from here, whatever section, or either you can choose, you can create your section here, or you can go for a type 2 and you can import your own section. Okay, so you can give your own section also. Similarly, tendon property, so you can define your own tendon property. Okay, so you can add. Okay, so this way you can add a tendon property. Okay, duct diameter, suppose. Okay, yield strength. So this way you can simply add everything, like all the tendon properties, tendon type, tendon name, duct diameter, ultimate strength, wobble friction factor. Okay, so once you, I mean, you can define your tendon type as a post tension, pre tension. Okay, so whatever, depending on the type, you get, when you see the results, you will get 2 types of losses. One is immediate loss, long term loss. Okay, so for post tension, when you go for post tension, you will get the curvature friction factor, wobble friction factor. Okay, so all this will come under the immediate loss. So whatever anchorage slip that you are given, so all the immediate loss will be calculated, right? You can also choose a relaxation coefficient as per ISA 112. Okay, so we can define it like this. Okay, so click on OK and close. So you can also give the jacking stress factor. So usually the tendons, they are jacked at 0.7 times of the ultimate strength. So you can define the 0.7 times here. Okay, or depending upon your factors you can define. Okay, similarly you can define the segments, anchorage position, anchorage number, how many anchorages that you are giving for bottom section or top tendon, the bottom tendon. Okay, you can also define a web tendon. So inside web, if you want to give a tendon property, then you can define a web tendon. Okay, so this way you give 2 cell, 1 cell section. Type 2 you can define manually, everything you can define manually inside it. Okay, so you can define manually the tendon properties. Yes, finally when we click OK, so we get our model somewhat ready. Okay, so this way, I mean, within just few seconds you get your model completely ready for with all the segments that you have created, all the works, all the sections that you have created. So peer section, since peer section doesn't look adequate, you can simply change it here. Okay, so this way you can change it. Also you can define You can check what has been done up till now. So supports, what supports it has given. Okay. Also the tendon properties, as you can see, 128 tendon profiles have been created. So automatically it gives a tendon profile also. Okay. So it has given time loads. So it has given time load. Time loads is for again for the 60 days that you remember I gave pair 1 at 0 day, pair 2 at 60 days. So the whatever difference that is, the time difference that is there, you can check it in the time load. So 60 days time load has been given. Okay. Similarly, self weight has been given. The form tabular load, you can see the form tabular load also. This is the form tabular load. Okay. So you can find out from stages, it has automatically created a number of stages also, like CS1, what has been activated in CS1. Okay. Similarly, CS2 when we go. Okay. So this way, what happens in CS2? Okay. So in CS1, peer table and peers are activated. Then the next segment in CS2. So you'll find that the form traveler, what it does is that in here, what it does, there is one form tabular load here. Okay, so this is suppose my form tabular. Okay, so it creates a cast for the next segment. Okay, so it creates a formwork. It pours in the wet concrete inside. So this is my wet concrete. So currently the wet concrete, when it is poured inside, it doesn't act as a structural member. So it is not acting as a structural member, it is not involving in the transfer of forces. So in that case, wet concrete is given as a load over the pier. So this wet concrete finally it comes over the thing as a load. Okay. So in that way it is done. Okay. So finally, so this way the full balance cantilever construction is done. With all the tendon profiles ready in front of you. Okay. Similarly, you can explore other wizards. Like I showed you FCM bridge wizard. Similarly, we have a cable state wizard. So in this also you have your full section layout ready in front of you. You just have to enter a few things and your section will be ready. Okay, so you can do FCM wizard. You can also do a simple FSM bridge, a simple PSC box bridge. Okay, so you can enter the section again, section properties, the tendon properties. Right, you can enter this like in this way. So you can choose a bridge material. So you can add a bridge material like this. So concrete bridge material I am choosing. Choose ISRC M40. Okay, so this way you can do. Then fixed support. Okay, then similarly section. So you can add your own section here, or you can just enter a section property. Okay, then again tendon. So you can give the inflection point and everything here. What is the inflection point? What is the tendon property? Again you can enter the tendon property in here. Okay, so you can add IRC 112 and then click on OK. So once you click on OK, your model is ready in front of you. Okay, so in this also you can see the construction stage has been done. Okay, and that too stage pre-stressing has been done. So whatever pre-stress you see, okay. So the section properties has been given self-weight. Okay, so this way it creates the section within one go. Okay, so this is wizards for you. Similarly, you have RC frame box wizard. So you can create your box culvert from here. Directly you just enter a few things like enter the dimensions of the box culvert, the span information, how many spans are there, continuous spans. Similarly, transversely, what is the layout of the box. Okay. Similarly, loads, you can define loads also. You can choose axis 6 and all. From there you can define the pavement thickness, what is the pavement thickness, what is the weight density of the pavement that you are taking, what is the soil weight density, surcharge, okay, underground water, barrier, sidewalk, okay, the system, the temperature gradient that you are taking. Once you do everything, you click OK, your box color will be ready in front of you. So in this way you can have the wizards for almost everything that you want to do in your bridge. Okay, so for our bridge, what we are doing is that we are creating this section. Okay, so we will be creating this section property first. So I will just show you how easily you can create the section property. Okay, so you can go to first save as something. So we'll just save as PSC box. Okay, then you'll go to properties, section properties. So you can either go to properties and go to section properties, or you can go to properties from here and then go to section. Okay, so you can go to properties, section properties, then click on add from the section. So you can find a lot of section properties here, like for database and user sections. So default sections like I sections, T sections that you are getting. So you can choose any code like IS code. Okay, and for that different T sections that are there in the code. So all the codal database things. So all the codal database things that are there, okay, can be done. Similarly, angle sections are, channel sections are there. Okay. And when you are, sometimes what we do is that we have our own section properties, but we don't have any save. So in that case, we can directly enter the properties inside the properties box. So you can enter the section properties. So whatever section property that you are giving, like T section, channel section, solid rectangle, and any section property that you are giving, you can put inside this. Okay, like 1 and 1. So you can just change these values. So it becomes a value section, typical kind of value section. Similarly, we can have an SRC section. SRC section again is a steel reinforced concrete section that we are talking about. We can also go for a combined section like IC combined, 2 channels combined together, 2 deep web. Okay, with a web plate inside. Similarly, PSC 1 cell, 2 cell. Okay, so we can create a PSC 1 cell, PSC 2 cell, 3 cell, PSC n cell. So you can also give a voided slab section. If you have a voided slab, in that case you can easily create a voided slab section here. Okay, and go for grillless modeling then. We have a tapered section property. So we can taper it from I to J. So we can go for tapered section property and composite section that I was defining before, that we have a slab plus girder system together. Okay. So for our purpose, we'll go for PSC sections. So we'll go to PSC 1 cell section and suppose name it as support. Okay. Since we have one haunch, okay, so we can define number of joints also. So it is up to you what type of profile you are having. So if you have some profile like this, and you're having a number of haunches like this, so you can provide these haunches also. So depending upon the profile, you can give the joints. You can activate the joints like this. Okay, so you can activate all these joints. So currently I will just activate one joint 01. HO2 I am giving 0.25. So whatever the section properties that are there here, I am giving that only. So 0.25 is there. 0.25. Okay, so whatever section properties that are there, I'm just simply giving it there in the software. Okay, so HO2 1 is 0, so through 2 is 2, side 1. So you can simply just enter all these values. Okay, similarly BO1 you can give 1.5. It's 2.5. Okay. 5. Here it is 0.375 and BO3 is 2.5. Okay. Similarly BI1 can give 2.5. So the section is created in front of you. Also, for the purpose of design, there are some things that are given here. So these factors are also there when you are defining a section on from AutoCAD, you are importing into Midas Civil. So in that case, you can give these factors. So it will be used in design. So basically, Z1, Z2, Z3 are the topmost fiber of the web and bottommost fiber of the web. Similarly, T1, T2, T3 is the total web thickness that is coming at each and every location. Okay. So at the topmost fiber, what is the total web thickness that is coming? The bottommost fiber at the centroid. So you can just click on auto for all these things and change the offset from center to center top. Why did we change the offset to center top? Because more or less we are tapering somewhat like this. I will just explain you that my actual element is a line element, simple line element. Okay, so suppose if we want a tapering of a rectangle, okay, and we want to taper it something like this. So my top surface is uniform in that case, right? So my top surface is uniform in that case. But if we give center, what it will do? It will taper from center to center. So it will taper in all directions. It won't be uniform properly. So what we do is that we just give a center top offset. So what happens once we just display centroid? You'll find that the centroid remains in the same location. The only thing is that the line element is shifted to the top of the section. So it won't affect any of the results or anything. Only for the visualization purpose, we can give a center top offset. So the line element will be aligned with the top surface of the section. Okay, so we will give a center top offset. So once we click on show calculation results, so you will find that all the results are calculated automatically. And once we close it and then we see here, it also calculates automatically the values for shear check and web thickness, the total web thickness that is coming. Okay, so we click apply, so support section. Similarly for mid section, we'll just give a smaller section. Okay, so this becomes a mid section. Okay, apply. Then we do a tapering. We go to tapered section, and we can taper between homogeneous section properties there like this. So we can taper between PSC one cell to PSC one cell. We can also taper otherwise also. Okay, so we can give here, suppose I'm tapering it from support to mid. Okay, so I can import size I, can import size j. Okay, now what do you mean by size I and size j is that majorly my modeling philosophy, whatever modeling philosophy that I am doing is that I create a node first, right? I create a node at one location first, I create a node at another location, and then I create an element from first node to the second node. So suppose this is my first node and suppose this is my second node. Okay, so now the modeling philosophy is that I am creating my element in this direction. Okay, so my software automatically understands that this is my ith end and this is my jth end. Okay, so I have to taper it from the ith end to the jth end. So basically, I have to give which section comes with the ith end, which section comes with the jth end. In our model, that ith end is now support. So we'll have what section here? We'll have support section here. Okay, at the jth end, we are having mid section. So we'll have a mid section. Okay, so we can import the section properties. So directly we can import the support section first, and for the size j, we can import the mid section. Okay. And we can give a z-axis variation as parabolic. So okay, so this way it defines the parabolic variation of the. Similarly, we get a offset. We go to center top again. Click on OK, display centroid, and click apply. Okay. Similarly, we give mid support. Okay, so we give a mid support section. So again, for mid support, what we'll do, we'll just change mid here, and for size A, we'll change support. Okay, so this way we'll do mid support section, and then we click on apply. So we got our 4 section properties: support section, mid section, support mid, and mid support. Okay, so now what we have to do is that we have to start with we have to give a material property. So to give a material property, we can just shift back to the material, click on add. So from here, we can choose what type of material we are doing. So we are doing a steel material, or a concrete material, or an SRC, steel reinforced concrete. It will be a composite material that will be defining, or a user defined material. Sometimes we are having some user defined properties, so we can enter the user defined material. So I can choose concrete. So once I choose concrete from the standard, I can choose ISRC. So ISRC is basically Indian code for reinforced concrete. Okay, so we can choose PSC M40. So usually for the PSC, we don't have weight density of 23.6. Okay, so I can choose by to none here and type 25. Okay, so I can choose this. This way I can create my own. I can just change the values that are there for default values that are there for the code. Okay. Similarly, once you see here that we have a plasticity data. So if you are having a plastic material, sometimes like if you are having a masonry material kind of thing, in that case you can include the plastic properties of the material also. Okay, and by default it takes a damping ratio of 0.05. So while you are doing while you are doing the analysis, the response system analysis and everything, in that case if you don't introduce the damping methods, in that case it will directly take by default 0.05. So click OK. Okay, and then close it. So you can see from your workflow that you have entered one girder property, material property, and 4 section properties. All are highlighted in blue. That is because we don't. So I will answer your queries at the end of the webinar. Okay, sir. Or whatever query that you are having, I will just answer at the end of the webinar. Okay. So section, we have defined 4 section properties. So support section, mid section, support mid support. So all are highlighted in blue. It is highlighted in blue because we haven't assigned it to any elements. Okay. So this way we have to assign, we have to create elements, we have to create nodes, we have to assign it also. Okay. So what we have to do, we have to first create our model. So for creating model, we can go to nodes, create nodes. Okay, suppose I am creating nodes at 30 distance. 30 times I am copying it. 1. So this menu will mean that the first node that will be created, it will give it a number of 1. It will start from 1. Okay, the first node it will create here. It will copy that node 30 times. Okay, at a distance of 1 each. Okay, so this is what it means. So if I click apply, so it will directly create all the nodes together. Then we go to elements, create elements. Okay, we check on insert node and element. Again we just click here and we click at the last. Okay, so once we have done that, the simple model is ready in front of you. But the thing is that we haven't included the tapering. We have simply given one section property, that is the support section. So all the elements are having only the support section property. Okay, so if you double click support section, you will find all the elements are being highlighted. So in that case, I have to assign different properties to all the elements. Okay, so I go to top view and I go back to the hidden view, that is the wireframe view, and I have to select the 5 elements. Okay, so I have to select the 5 elements. Okay, so these second 5 elements I have to give a section property of support mid to it, right? So usually you yourself, how will you assign a property to a section? You will first go to the properties, you will go to the change element properties, and from element properties then you assign it, then you change the property. It is a very cumbersome process in to do it. Okay, so in Midas Civil what you do is that, okay, you can choose the support mid section and simply drag and drop here. Anywhere in the workspace, simply drag and drop. So I can just drag and drop. That's it. Okay. Similarly, I can choose the mid support section. Okay, this will be these 5 sections that are there. So I can just simply mid support. I can just drag it. Okay, and drop it anywhere. So this way I do the so support section we are having now we are having a here. Similarly support mid we are having here, mid support we are having here. So I have to give mid section now. So I can unselect this section. So I will just unselect this section. Okay, and drag and drop mid section over it. Okay, so this way our section assignment is over. So once we go to the solid view, you will find that all the section properties are given, but you are finding some rough adjustments here, right? So these adjustments are some rough adjustments, and it is plausible. It is plausible because the Midas will identify each section as a separate section, right? So each of these sections will have its own I and own J, right? So whatever ith and jth property tapering that we did, it will taper it from its own ith section property to its own jth section property, right? So in that case, we need to give our own. We need to generate some tapering properties. Okay, so what we have to do, we select mid section, we select support mid. Sorry, we go to properties, tapered group. Okay, so we here write support mid. Okay, and then we click on, because if you carefully see this diagram, okay, the tapering is done from this plane. So this plane, the tapering is done. Okay, so whatever tapering that is done, that will be done in this direction, right, from J to I. So I will just give polynomial of 2 degree. Polynomial of 2 degrees. Okay, so polynomial of 2 degrees. So we will get from I to J, from J at the distance of 0 meters. Okay, and then we click add. Okay, so this becomes completely tapered. Now for the next section property, okay, so these are the section property. So in this case, I can again choose from I name it as mid to support. Okay, and then click on add. So this way our tapering is smoothed again. So now once we click this, we click on convert to tapered section. Okay, so automatically it will convert all those sections into individual section properties, and you can just right click anywhere, go to properties to find your tapered section property that you have given. Okay. Okay, so this way you can give. So once you have done this, next we give some boundary conditions. So we can give some boundary conditions. We have to translate these nodes to the bearing nodes. So we can just translate these nodes somewhere in dy, suppose at 2.3 meters. Okay. So unequal distance we can go. We can go to y. So 2.3 and minus 4.6. So what it will do? It will simply translate these nodes in both the directions. Okay. So similarly, we can just select the recent entities that we have done and translate these nodes downwards. So we'll click on Z and we'll choose minus 2.5. So once you have done that, if you go to the left view, you will find that the nodes are exactly at the bottom of the sections. Okay. So now what we have to do, we have to define some support conditions to it, right? So support conditions, now although you will find that the solid section is actually over the nodes, but actually when you come to the wireframe view, there is nothing that is connecting all these nodes. So we have to connect these nodes together. Basically, we have to connect these nodes together for a proper transfer of forces. Okay, so we have to tie these nodes together. So to tie these nodes, we have a special kind of boundary constraint that is called links. Okay, so what we'll do, we will go to boundary, elastic link. So we'll give an elastic link. So elastic link, by the name that is suggested, is that we have so in elastic link, what name that is, that the name, by the name it suggests that it is an elastic. It is having elastic properties, which is having its own stiffness matrix. The stiffness matrix is defined by U. So you give your SDS value, SDY value, stiffness in X direction, stiffness in Z direction, rotational stiffness. Okay. So in our case, we'll just choose rigid. So rigid by default, what it does, it gives a very high stiffness to the elastic link. So in a way, it behaves as a rigid body. Okay. So I can just copy this elastic link with the distance 30 meters. Okay. So this way we can copy it. Similarly, we can also provide another type of link. Another type of rigid link that we are having is rigid body link. Why I call it what is the difference between that rigid and the earlier rigid link? As you remember telling you that the earlier rigid link was an elastic rigid link. Okay, so it was having an elastic property. However, this rigid link is having a completely different behavior. In this rigid link, what happens is that we have two kinds of nodes. One is your master node and one is your slave node. So this becomes my master node and this becomes my slave node. So whenever I connect it with the rigid link, what it does, it creates a rigid body in between. So it creates a rigid body in between master and slave. So virtually it creates a rigid body in master and slave. So whatever translation that it is, whatever deformation that it is having, it will also have the same deformation. So that's the perfect rigid body. Okay, the behavior is different. However, the way of acting is different. However, the final result will be similar. Okay, so I will just select the slave nodes. These are my slave nodes. I will select the master node in between. Okay, I will click on rigid body and copy elastic link. Okay, copy rigid link, and in the X direction we will translate it to 30 meters. So it directly copies the rigid link at 30 meters to the other end. Okay, so this way okay. Finally, we have to give some support conditions. So for support condition, I have to choose this node first, boundary define supports. So I will choose a normal support like this. Okay. So what is happening is that currently the support condition that we are giving, usually when we do theoretically, we are having one line element, right? We are having one support here, pin support, and we are having at the other end we are having a roller support for a simply supported conditions, right? For a simply supported condition, we are having two kinds of support. One is a pin support at one end and one is roller support at the other end. Okay. So in our case, what we do is that in this also we will do that only. So this will be our pin support that we are giving. Okay. So what we'll do, we'll allow this node the translation in x direction, because for temperature stresses we need to get release in x direction. Okay. Similarly for this node, because this is having a y degree of freedom, so it will be given a translation of y direction. Okay. And this node will also be given a translation of x direction. And since it is in the y direction also, so it will also be given a translation of y direction. So this way we define a support condition in a breast, I mean in a 3D breast. Okay. So we'll just choose the second node and we will release dx. Okay. And choose this node and we'll fix dx but release dy. And this node will just release dx and dy, both the ends. Once we have done that, we'll have a full breast, something like this. So the modeling is complete. Okay. Next, what we have to do is that we have to give some pre-stressing. So pre-stressing, again we can go to load. Okay, and we can go to temperature of pre-stress. So before that we have to first add some load cases, right? So we have to go to static load cases. So we'll add some self weight and we'll give some dead load type to self weight. Okay, so this way we'll define the dead load type. And similarly we define SIDL load. So we can define SIDL here. Okay, so dead load of component attachments. And similarly we will define pre-stressing. Okay, so pre-stress, click on add. So in this way we define 3 load cases. We are giving dead load type and dead load of component attachments. So whatever you are seeing here, that is in the brackets. Okay, whenever you are doing a load combination, your auto live load combination, auto load combination, in that case the software, the code will identify D, DC, PS. So according to that, it will automatically give the factors that are there in the code. Okay. So and one more load case is there, that is construction stage load. I will define the significance of this load after some time. Okay. So once we have done this, we can go to load and define self weight first. So I can define minus self weight. Also, since we will be doing construction stage analysis, so we can define load groups. Since we have to define load, we have to activate some loads in some stages. So we have to define those loads in a particular group. So we will define the group. So self weight will add a group. Similarly, SIDL will add a group. And pre-stress will add a group. So this way we can add a group. Okay. So we'll assign self weight. We'll give -1, click on add. So this way we have assigned the self weight. So -1, what it will do, it will automatically So since the weight density that we have given already in the material properties, we have defined some weight density, that is WC. So it will automatically take -1 factor and behind the and -1 into WC. So whatever weight that has been given will be considered. Okay, weight density that has been given, it will calculate the self weight according to that. Similarly, element beam load we have to give. So element beam load we have to give it as an eccentricity from the main element. So I will just choose SIDL from the group name also. Okay, and then eccentricity. So from offset I can choose an eccentricity at a global Y or local Y. Okay, IAT I am giving an eccentricity of how much? Suppose because the total base was 9.75 meters. Okay, so it will be around 4.75 something. So at 4.75, so you can either choose global Y or local Y. Since it is not a curved base, so the local Y-axis will be aligned along the global Y-axis. So there is no need of giving a global Y or local Y. I mean, you can give anything. Similarly, global Z. the loading direction. I can give here. So this will act in one end. Similarly, we can again choose all the section properties and give it on the other end. Okay, so this way we are activating SIDL for the railings on both the ends. Okay, so the eccentricity that we have given is given according to offset. So offset means wherever that the line element is there, it will give an eccentricity about that line element. Okay, on both ends. So if we have a direction local y, so it is giving in local y direction what is the eccentricity that is there. Okay. Similarly, if we had selected centroid instead of offset, so where the centroid is locating somewhere here, so it will have given the eccentricity about the centroid. Okay, so this is the difference. Once we have done that, we are left with pre-stressing load. So we'll go to load, temperature, pre-stress. Okay, tendon property we'll add. So we can add a tendon property like tendon. If you remember, I showed you in the while we are doing the wizards also. So we haven't defined any tendon material property. So you can add a tendon material property from here. Okay, we can give a steel material property. So ISS suppose 540B, but since tendon is not a structural steel, remember it's in high. It has got very high tensile strength. So for that case, we can change the elastic modulus of elasticity for the tendon. Okay, this way we can change. Okay, and then we click on OK, close. We choose tendon from here. Tendon area, either you can enter it manually, or what you can do, you can enter it from strand diameter. So you have the strand diameter like 12.7 mm. Suppose 19 strands I am giving. So I can give 19 strands here. Click on OK. So automatically it will calculate the total strand area that is there. Duct diameter for a 13T19 is around 100 mm according to the code. So we'll give 0.1. We'll choose IRC 112. Okay. So we can give some ultimate strength property like this. Okay. So curvature friction factor, the wobble friction factor I can mention. Similarly, anchorage slip is usually 6 mm only, so we'll remain it as 6 mm. Okay. After we have done that, we can enter a tendon profile like this. Okay, so we will enter a tendon profile on both ends symmetrically. So whatever like this is there, so we are going to enter a tendon profile somewhere here, here, and here. Similarly, on both ends symmetrically, I am going to enter tendon profiles. Okay. So we are going to enter around 6 tendon profiles. So we can enter T1 assigned elements. We can select all the elements. Okay. So we can either enter as a plan and elevation. Usually you have in AutoCAD you have some plan of the tendons and elevation of the tendon. So you can define your plan here. This is your plan and this is your elevation. You can define your elevation. So if you have an Excel sheet of the of tendon profiles, okay. So what you can do, you can directly copy those tendon profile and paste it here. Okay, so you can directly copy and paste. Okay, using Control D. Okay, so this is quite a simple way. So you can go to 3D. Okay, so this way you can define the tendon profiles. So you can define like 0 at minus 1.2 meters. At 30 we are giving. Okay, so currently I am defining straight. You can also define a symmetric tendon. Suppose you have a tendon property like this, somewhat like this, and suppose you have a tendon property somewhat like this. A symmetrical property. So what you can do, you can, whatever tendon profile that is here, you can make a symmetric tendon on the other side also. So you don't have to enter the full tendon profile for the full brace. You can enter up to the half brace and you can directly make a symmetric tendon for the rest half. Okay. So profile insertion point, I can give this as the profile insertion point, and offset Y, I'm giving it as 2.55 meters suppose. Click on apply. So this way my first tendon is done. So we can similarly do the other tendons like T1R. Okay, so I can give minus 2.55. Okay, so T2L. So I can change these values according to the tendon profile that is there. Okay. So T2R I am giving it as minus 2.45 again. Okay. Then again change this value to 1.8. Okay. And T3L. Okay. And minus 2.35. So we can give it R. Apply. So this way we enter tendon profiles throughout the sections. Okay. So now we have to go to pre-stitching. We have to jack the tendons. So we'll go to tendon pre-stitch. You'll find that whatever all the options that are in Midas are majorly from left to right. So it is very easy to understand. Like for a normal modeling also, first you do node element, then you can give property, then you can give boundaries, then you can do loadings, analysis, then results, and then this is the design portion that you are handling. Okay. Similarly for a tendon, you can directly go to tendon property first, tendon profile, then tendon pieces. So everything is from left to right. Also, yes, sir, for a tendon profile, we actually are having a new feature that is called that is PSC with tendon template. So it can automatically generate the tendon profiles. So you can select the elements, you can assign it, you can choose a curved profile like this, somewhat curved profile like this. Okay. So then you can provide from where to start, at what end. Okay. Then you can provide a number of spans. Suppose here is one span. If you have 3 spans. Okay. So once you click OK, that way you can generate an automatic. This is an automatic tendon template that we are having. Okay. So you can generate a tendons using this also. Also, sir, when we are doing a lot of lot of wizards when we are doing. In that case, what happens? We have you must have seen FCM wizard, FCM wizard when I was showing. It will automatically generate all the tendon profiles also. So there also the software will automatically generate the tendon profiles. When you are doing wizards, you will get those options there. Okay. So for now I am going pre-stressing. I'll choose all the cables here. Okay, so I can choose either stress jacking or force jacking. So I am giving a stress value on both ends. The jacking force is usually 0.7 to 0.75 times of the ultimate strength. That will come around 130 to 000. Similarly, I can give it in the end, okay, and add it. So this way, my tendon profile has been given. Next thing is to define the moving load. Usually, because this brace is around how many meters? It is around 10 meters, more or less. So if we define suppose 1.25 something at the ends, so remaining length for the carriageway will be around 7.5 meters. Okay, so this will be around 7.5 meters. Okay, so what I have to do is that I have to define some lanes accordingly. So where we have to define a class 70R lane and 2 class A lanes. So class 70R lane with minimum eccentricity. Similarly, 2 class A lanes according to the load combinations that are there. Okay. So I will just go to load, moving load, choose India from here. I will add a traffic line lane first. Okay, so lane 1 I am giving lane 1 name. So lane suppose 70R I am giving. Okay, so eccentricity, we have to calculate the eccentricities. So for now what I am taking it that I am taking it as minus 1.15. Okay, I think it will come around that only if you calculate from one end. So from one end you can subtract the curve length, the class barrier length, okay, and then you can give you can define a class barrier length, and you can define then, you can give the spacing, minimum distance between the curve and the wheel, that is about 1.2 meters. So you can come around what is the placement of vehicle. So to define the eccentricity from the center of the bridge, because the line element is aligned with the center top. Okay. So span length I am giving it around, suppose what is the span length? 30 meters. So this span length is to define the impact factor. Okay, so whatever impact factor that is there. Okay, so lane element, cross beam. So this is a vehicular distribution, because we can define either a lane, because we are only working with one lane element. So whatever moving load that is there, so whatever moving load that is coming here, okay. So whatever moving load that is coming here, it will be transferred to the lane element as a force and as a moment. Okay, so this is a lane element distribution. But if we are having suppose, so we have to define lanes, because we need to tell the software that where my vehicles will move. Okay, sir. So we have to define lanes for the vehicle. This is not defining vehicle. We are not defining any vehicle. We are defining the traffic lanes. Okay. So we'll just define our lanes. So this is my 70R lane that I am defining. Okay. Second. The wheel spacing should be 1.93. Okay. Similarly, we can define a class A lane. So one should be around 2.2 something. So one class A lane is there. So I will just define. Okay. Second. This should be 1.8 meters. For a class A, the wheel spacing is 1.8 meters. Okay. So this is our class A lane. The second class A lane will be, we have to calculate it. It will come around 1.05 at the other end. So 1.05 means at the other end, what is so the eccentricity is now at this end. So positive eccentricity is somewhat, which is on the right hand side of the lane that we are defining. Okay. So we'll again, so apply. So this way we defined 3 lanes. Okay. So we can just right click here and display. So these are the 3 lanes. So if we just move in closely, you'll find that the wheel spacings are given here. So somewhat here it is given. Okay. So this is the wheel spacing. Similarly, these and this. Sorry. This. Okay. So these are the wheels that are given. So based on the. Okay. So based on the lanes that we have defined, you have to define the vehicles also. So you can define vehicles, you can add standard vehicle, so you can define a class A vehicle. Similarly, we can define a class 70R vehicle also. So, okay, so you can add user defined vehicles. Okay, and then you can close it, or you can add a user defined vehicle like this. Okay, so we are having moving load cases. So we can add a moving load case. So we can add MBLA. We can of course go for auto live load combination, that is there. So some of us are asking, why aren't we going for auto live load combination? The reason is because, see, usually what happens is that the software doesn't identify that there is a minimum eccentricity of class A lane. Okay, and there is a minimum eccentricity of class 70R lane. So when it is doing an auto live load combination, the software will also run a class 70R lane on a minimum eccentricity of class A lane. Understood, sir? So if we are having 3 lanes, in that case the problem comes, because in that case when the class 70R is running on its own minimum eccentricity, class A is running on its own minimum eccentricity. But when the software will do, what the software will do, it will run class 70R in class A lane also, class A on class 70R lane also, and finally, see what happens is that the minimum eccentricity for class 70R is more than that of than of class A. So in case the class 70R is run alone in the class A lane, you will get more critical result, right? So that will be a little wrong adjustment. So I have already referred it to the headquarters. So most probably this will be sorted out in the next version. Okay. So usually whenever I am going somewhere, I usually prefer not to do the auto live load combination. Okay. So I will just uncheck the auto live load combination. Okay. So I will just uncheck the auto live load combination. So I'll just go to add. Okay. So for now, what we do is that we'll just run class 70R separately on a 70R lane and both the class A lanes on together. Okay. So class 70R we are giving a minimum as 0, maximum as 1. We'll choose class 70R here. Click on OK. Okay. So moving load for 70R. Okay. So we'll click on apply. Similarly, we'll choose a class A lane moving load. Click on add. Okay. And we'll choose both the class A lanes. Number of lanes we'll choose as 2. So 2 lanes we are now defining. So whatever combination that is there according to code, we will define both the lanes. So what it will do, it will run first one vehicle in class A, first class A lane. It will run this again the same again class A lane. It will class A vehicle will run in the second lane, and then it will run it on both the lanes together. Okay, so these are the combinations that it will do, and then we'll click apply, and then we close it. Similarly, for a concurrent reaction, we usually are interested in a concurrent reactions. That is, suppose for a particular position of vehicle, I'm getting maximum reaction here. Okay, so this is my suppose R max for a particular position. So what that position of vehicle, what is the reaction on the other ends, other reaction. So these concurrent reactions, I can, for that I have to create a group. So I will just create a group. Okay. So these are the concurrent reaction group. So I will just write concurrent add. Okay, and select. And I will just select the bottom nodes together and choose concurrent here. Okay, so this way we define the concurrent. So all the nodes that are for the reactions we will choose. Next we select the concurrent reaction group, click on OK. Okay, so this way we define. So for the moving load, now everything is over. Okay, so for the moving load, everything is over now. So now next what we have to do, we have to do a construction stage analysis. So for construction stage analysis, as you know, that we have to do proper groups. We have to define groups first. So we'll go to groups and we'll define few groups, like structure group, we'll define one structure group. Similarly, boundary group and 3 load groups that we have already defined. So now what happens in the construction stage, I will just explain a little bit of construction stage. So okay, so what happens is that suppose I have a precast, this is my manufacturing plant. At one end, suppose I am having a manufacturing plant, and this girder that you are seeing on the on your screen, suppose this girder was casted some times before. Okay, suppose it was casted 7 days before. So 7 days. So 7 days it was in manufacturing plant. So on the first stage, okay, on the first stage, this section is brought over into the construction stages, right? So I mean, in the first stage, this is placed over the bearings. Okay, so on the first stage, my age of the member, it becomes 7 days. right? So on the first day my age becomes 7 days. So in this way we do the construction stages. So what we have to define? We can define a stage. Just look at it in this way. Then how can we define one stage? Okay, so we can define one stage by the element that is being activated there. Okay, we can define same thing. We can define a state by the boundary that is over which it is being activated, and we can define what are the loads that we are activating. Okay, so in this way we can define the construction stage. Okay, so the element is actually the superset of all things. So until and unless the structural element is there, we cannot define we cannot define a boundary condition. We cannot define the loadings. Okay. Similarly, we have to define some boundary conditions. So you have to define some boundary groups. Also, sometimes what we do is that we do pre-stressing. So we do pre-stressing in some stages, right? So suppose what I am saying is that suppose at the first stage, suppose when the concrete of the girder concrete, it attains 17 days age. So at the age of 17 days, I am doing pre-stressing. Okay. So in that case, the pre-stress should be activated on the 10th day of the construction stage. Why? Because on the 10th day, my age of the concrete will now become 10 plus 7, that is 17 days. Okay. So this way, we first define our construction stages first, and then we go about construction stages. Okay. So we can go to load construction stage. CS1 will define age of our structure as 7 days. Boundary will define as boundary group. Pre-stress we have to define it in the 10th day, but we don't have any first or last. We don't have any 10. So in that case, I can define 10 here. Click on add. Okay. So I can now just give 10 here. Add. Self-pit also I am giving at the first day. Click on add. So first stage duration, let it be 30 days duration. Okay. So this way we'll click on apply. My first stage is over. The second stage, suppose on the 60th day of the construction, I am activating the SIDL. So SIDL will be activated on the last day of the second stage. Okay. Also similarly, we can define stage 3 with a 10,000 days duration. That is for a long-term effect that we are seeing. Okay. So this way we can define 3 construction stages. Also we have to assign the elements in the groups. So we'll select all the elements. Remember that we have to select the boundary elements also in the element group, because as I told you, the element group is the superset. I mean, it has to include the boundary nodes, otherwise the boundary condition won't be defined. So I will just drag and drop like this. Similarly for boundary group, I will select everything and drag and drop boundary group. So once I drag and drop boundary group, all the boundaries related to the element that is selected will be automatically selected. So we'll just click OK. Okay. So once we are done with the construction stage, you can go to CS1. So CS1 you will find that no SIDL is activated, right? CS2 you will find that the SIDL is now activated. Okay. So this way you can check if the construction stage is properly done or not from the tree menu itself. Also we need to define some time dependent material property. So to define time dependent material property, you will go to properties, creep and sinkage, click on add. So we will write here CNS. Okay. So we will give the concrete strength property 40,000. Notational size is usually it is the area of the section. I mean, it is a total length of the section that is being exposed to the environment. So usually it is given from the formula. It is given here, that is 2 AC by U, or you can give it as 1 meter here. So once you click on show result, you will find the creep and sinkage, creep coefficient, sinkage strain. Also you can choose the code. So I can choose the code as IRC 112. Okay, so we click on OK. Similarly, we can define the compressive strength. Click on add. Okay. Choose IRC 112 again. Okay. So you can choose normal cement from here. redraw graph, click OK. Okay. So now we have to link both these material properties. Okay. So as you can see from the worksheet behavior only, these time dependent material properties are highlighted in blue. So it means it has been defined, but it hasn't been assigned to any material yet. So I will assign it to material using material link. Okay. So I will choose CNS compressor, girder, add, and then close it. So this way we assign the time dependent material property with the girder. Once we have done this, we have to now control our analysis. So we have to go to analysis. So this section is the complete control for the analysis. So what features do we want to analyze? How the analysis should be performed. So everything will be controlled from here. So I will give you moving load. So these are the influence generating points. At what spacing do you need the moving load to be incremented over the bridge? So number per line element means at every line element, at every 1/3 position, the vehicle will be placed. Okay, so this way it is done. So we can give 3 here. Normal plus concurrent forces. Okay, calculation filters is usually very effective when you are having very long bridges. This is a 30-meter bridge. So at max only one vehicle or two vehicles will come. Okay, but if a very long bridge is taken, like around 600 meters something, in that case there will be a lot of vehicles that will be coming. In that case we can select a particular critical element according to my engineer experience. So you can just select a particular element that is where the most critical result will come, and we can just check the results for that. So that is our calculation filters. Okay. Similarly, bridge type for impact calculation. The impact factor is calculated on the basis of RC bridge or steel bridge type. So based on the span length that you have given, you will give the impact factor. It will generate the impact factor automatically. So maximum successive vehicles is let it be 2. Okay. Also, you have to do construction stage analysis control. See, self-weight and SIDL will be shown together in the construction stages. So in the dead load only. So what I will do, I will just separate it out. Okay. And click on OK. Also one more thing now, that when we went to static load cases, I defined self-weight, SIDL and pre-stress separately. Right. I told you that there is one more type of load case, that is construction stage load. Okay. Okay, so what happens is that it is usually preferred to do construction stage, to modify it as construction stage load. I will tell you the reason why. In a few moments I will just tell you the reason. Okay. Okay, so once we do the analysis now, so the reason is that because when we are defining it as a dead load, that load will also come in the construction stage dead load, and it will also generate a static load case of dead load. Okay, so when we are doing auto live load combination of construction stage and static load, so it will add up the dead load from the construction stage, and it will add up with it, it will add a factor of static load also. So when we are doing design, actually we are designing for 2 times of dead load. Okay, so whenever we are doing construction stages, whatever loads that we are activating in the construction stage should be given a construction stage type. So now if you see, if I go for forces beam diagrams, okay, we are in the post CS, that is the results which are shown out of the construction stages. So when the results are shown out of the construction stages, you won't find any self-weight, SIDL or pre-stress here. The reason because it was defined as a construction stage type. So now if we do a auto load combinations, so in that case, even if it takes, it won't take any static dead load for combinations. Okay. So we can check moving load max, results for moving load max of 70 R. Second, sun display the names. Okay. So you can check the results. Okay, also for suppose this is the maximum, as you can see, the maximum is coming at around 15th element. So I can check the using mobile of tracer. I can check at the 15th element what is the vehicle, how the vehicle is looking. I mean how the vehicle is placed. Okay, so I can convert this vehicle into a static load again. Okay, so this way we can backtrace the vehicle. Also, we can find construction stage results like forces, mean diagrams for dead load. So this is for the self weight. Similarly, for the erection load, because SIDL is not activated here, so SIDL is not given activated in the second stage. So it is defined in the second stage. So differential temperature analysis is usually we have to give a loading here. So if you go to load, temperature and pre-stress, you can give a temperature loads. So you can give beam section temperature. Okay, so PSC and composite. Then you can give from here what is from the top. You can give a positive. You know, you have positive temperature difference, reverse temperature difference. So in positive temperature difference, you can give from the top how much distance is there. Okay, I can give T1, TF. So you can give a varying temperature from here. Okay. So next, what you have to do. So very quickly, I will just show you the tendon losses also. Okay. So we'll go to results, result tables, tendon loss. So whatever loss that we are having, we'll very quickly find it here. Okay, so stress after immediate loss. This is the stress after the immediate loss of the tendon. Okay, this is the elastic deformation loss, that is due to the weight. This self weight, there is a moment. So mj to ej square by iy. So this will be there. Similarly, we have some creep and shrinkage loss. Okay. Similarly, under stage 3. Okay. So this will be how you can see the losses. You can also find the losses from somewhere here. So you can go to tendon loss graph and then you can animate it to find how the losses are occurring. Okay. So once everything is over, because it was I have to show the design also. So I will just quickly show you the design. So for design, first we have to make load combinations. So I have the results load combination. You can go to concrete design, auto generation. Of course, I said 2000 and 2010 is having some difference, so, but you can edit those afterwards. So we can just click on OK. Just a second. Results load combination. Okay. So I will just click OK here. Okay. So automatically it generates the various load combinations. You can edit these load combinations here also. Also, you can have your own load combination sheet. Like if you go to spreadsheet format, you'll find for all load combinations, this is an Excel sheet. So you can have your own load combination sheet there and you can import it anytime. Okay, so it's kind of a code, only you are doing it. Okay, so just click close. Now we go to PSC. So we'll design it by suppose Eurocode. So parameters. So we can define some parameters like modify define parameters. So Eurocode is more or less very similar to Indian codes. So you can change a few factors here to make it more similar to Indian codes. Okay. So you can give the stress limitation factors, pre-stressing steel factors. This is at the ends near the anchorage position in between. What is the stress? Allow the stress has to be there. Okay. So this way you can define. Similarly, select all, you can choose normal cement from here, click OK. Then we choose PSC design material. Okay, so we select the girder and we choose ISRC M40, right? Then we can choose, yes sir, you can add an additional bearing also. Okay sir, I mean you can add it as a temporary bearing, you can add those things. Okay. So whatever questions that you are asking, I will reply to all these questions in detail afterwards. Okay, because we are having some time crunch, so I'm not able to explain each and everything. But I will explain each and everything and I will give you a mail afterwards. you can, all of you, whatever questions that you're having, you can just give your questions here. I will reply to them afterwards through mail. Okay. So we can choose main rebar here, 250, and then close it. Similarly, we can choose design position. Suppose I want to design only a few elements, like these two elements I want to design. So I can just choose this. Similarly, output position. Okay. And serviceability load combination. So I can choose some load combination in frequent or quasi permanent is there. Okay, so I will choose all the load combination characteristic only. Okay. Then short term and long term. So you can define here some long term cases are there or short term cases. Okay. So in this you can define some long term, short term load cases that are there. Usually moving loads they are considered in short term load cases. Okay, so you can define it like this. Also you can define exposure class. So for exposure class for this particular element you can define different exposure class according to the Euro code. So you can define the different exposure class. Okay, so you can define it from here. Then you after all this you click on perform design. Okay, once the design is complete, then you click on Excel report. Okay, so once the Excel report is complete, okay, it will take some time to define the Excel report, but once you see the Excel report, it is very well-fledged Excel report. So I will just show you one Excel report that it generates. Modi sir, actually, if you want to have a temporary bearing in between, okay, so what you can do, temporary bearing means it will be there for some stage. In the next stage, what it will be there, it will be deactivated from there because it's a temporary bearing, right? So we are activating a particular boundary condition in the one stage. In the next subsequent stages, we will deactivate that boundary condition. Okay. The only difference that will occur in a temporary bearing and a permanent bearing is that temporary bearing will have an original orientation that is there. Permanent bearing, however, will undergo deformations because of the loadings. Okay, so we'll have a deformed type in that. Okay, so coming back to the design report. So as you can see, it generates a full-fledged design report. Okay, so it generates a full-fledged design report with each and every formula that is there. Okay, so what is the design strength of concrete, how it is calculating, what is the design strength of reinforcement bar. Okay, another thing that I haven't shown you how to enter reinforcement. So very quickly after this I will show you how to enter reinforcement also. Okay, so what is the force, what is the axial force that is there. Okay, total force that is there, what is the formula for each and everything. I mean, so it gives a very good design report, an excellent report it generates. It gives all the factors that it has considered. Okay. Okay. So in each and every formula, each and every clause, so it includes everything. So bending resistance, shearing resistance, the torsional shearing resistance is there, and torsional resistance is there. Okay. Similarly, tendon pre-stress. So it gives a very full-fledged design report of everything that is there. Okay. After this, these all things can be seen or here also. So this was for the PSC boxes that we saw that we did now. Okay. So the second. Okay. So you can check from the result tables also we can check the positive and negative value. So from here we can find the area of steel required. Okay, what is the area of steel required? What is the allowable strength? Okay, also if it is passing for shear strength or not. So currently it is passing for everything. Okay, so if it is not passing, it will show you in red. Okay, similarly combined shear and torsion strength. Okay, similarly it can check the cross section at the construction stage, the principal stresses, the tensile stress at each construction stage. Okay, also Yeah, sir, you can model in a curved base, you can do that, sir. Okay, you have nodal local axis, so you can change the local axis of the bearings according to the curve. Okay, so you can do that. And also you can give principles as in construction stages. Okay, so very quickly I will just show you how the reinforcement are done. Okay, so in this case you can find that there is one reinforcement given. Okay, so to give a reinforcement you can go to properties, section manager, reinforcement. Okay, and then you can click on span. Okay, then you can define either a longitudinal reinforcement or a shear reinforcement. Okay, and you can define the input method like centroid A or B. So we can define line method. Okay, so we can define here suppose 35 reinforcement at from this is the centroid, reference is centroid, right? So for y-axis this is the reference, for z this is the reference. Okay, so y we are giving 0, z suppose the cover from the top is 660 mm, we can give 0.06 here. Okay, the number we can give 35. Okay, similarly we can give spacing of suppose at what spacing we are giving, so 0.25 suppose I am giving. You can choose a diameter from here, so 18 diameter suppose I am choosing. Okay, so ultimately when we add it, it will define the reinforcement. Okay, so currently the reinforcement is too much, so we can change it again back to suppose 0.25, 0.2, like this. So this way you can define your longitudinal reinforcement. Similarly, you can define a shear reinforcement. You can define. Okay, so you can define diagonal reinforcement. So what is the pitch angle? So what is the pitch at which the shear reinforcement has to be given? What 90-degree area of reinforcement also you can choose here. Suppose dia is 7 mm, 8 mm suppose I have, and number of leg 4. This is a 4-legged thing. Then we'll click on OK. Okay, and then we can go to torsional reinforcement also. So this way we can either define the shear reinforcement or a torsional reinforcement and longitudinal reinforcement. After we have done everything, then we come to PSC design. Okay, so we can design it again. We can check for the reinforcement what we have given, if it is passing or not. Okay, I know there is a lot of things to explain in design and everything. There is a lot of things, and for 1.5 hours, it is. I mean, we cannot explain each and everything. I know you will be having a lot of doubts also. Okay, so I will just dedicate a little 5 minutes for doubts. So if you have any doubts now, I will just reply. Otherwise, what I will do, I will reply to all of your queries, whatever query that you are having. You can send us to techsupport@midascivil.com. Okay, you can send us to techsupport@midascivil.com, and any doubt that is there, we are really very happy to reply to you. Any case, I will just take some doubts now. So starting. So underground construction of diaphragm wall, yes, you can do. You can do events, but you can simulate that thing, Mr. Ankit Mittal. You can simulate that thing in Midas Civil easily, because Midas Civil has got some point spring supports. So in point spring support, you can give the soil stiffness that is there, varying soil stiffness, and you can do a construction stage analysis. Okay, so that you can do easily in Midas Civil, but for a very accurate analysis, I will request. I mean the GTS software, Midas Geotechnical is preferred. But yes, you can analyze it perfectly in Midas Civil. Okay. Murthy sir, I cannot. I mean, can you just explain what do you mean by Midas? Does Midas accommodate vertical profile for a single span press? Okay, can you just explain what is a vertical profile for a single span breast? I will be happy to reply to you. For this exposure conditions, yes, sir, you can define. As I showed you at the end, you can define the exposure conditions for the structure also. Okay, so you can define according. You can get some exposure class as per the standards. Okay, and similarly, some other queries are there. Second. Tendon profile, as I told you before, that for a pre-stressing profile, if you go for wizards, it will automatically generate a tendon profile. Okay, but also we have an automatic tendon generation thing. So maybe I will show you on some other webinar or something that how to generate an automatic tendon profile. Otherwise, you can always, when you are using a wizard, there will be an option to automatically generate a tendon. Okay, so tendon profiles the software can suggest a tendon profile. Okay. Parabolic tendon profiles, usually using that automatic feature, you can define the points of inflection and you can define the parabola. Also, if you remember in the FSM bridge, wizard, just a second. If you remember the tendon profile, so I showed you the inflection point and everything. So there you can give a parabolic profile. Also, similarly in the tendon generation, when I showed you the tendon generation thing, tendon template, so once you click on here, okay, so you can define here curve profiles here. So in this way you can define the inflection point, what is the inflection point and everything inside this. Okay, so the parabolic curve profile can be easily done, or the simplest way is that you can directly copy the coordinates from the Excel sheet and paste it. Moving mode query, I think I have replied to those. Regarding other combination, British code and everything, it doesn't have any problem for HA and HB loading and anything. It will auto combine according to what the code is given. So you don't have to worry about any other code. Only for Indian codes, I have already suggested it to headquarters to include that thing. Okay, sir. So only for Indian codes that there is some issue there. I mean, you can of course manually combine the loads, but auto live load combination currently for more than 2 lanes, it will give you some other results. Yes, sir. Vertical profile. By vertical profile, do you mean a vertical section kind of thing, or I mean, I'm not. You're meaning like piers or piles like this by vertical profile? Yes, sir. You can do that. Of course, you can do that, sir. Highway alignment and else. Okay. And so I will just end this webinar. We don't have so much time. So I hope you like the webinar. And if you have any questions, please mail us to tech support. Okay, I'll just write it in the chat box. So please mail us to techsupport@midascivil.com. Hope you liked the webinar, and we are very obliged to see so many participants. Thank you so much.